Okay, everybody. This is section 7-4. It's on inequalities and something called linear programming. And we're going to try and take what typically for us is a 4 to 5 day thing, and we're going to streamline it a lot. I'm going to let you use Desmos today, so if you have that available to you, that would be awesome. Either on your phone, or if you got a tablet, something like that, or you can use your computer. Just keep open tabs between the two things. So the first thing that we're going to talk about is what exactly do inequality solutions look like. So x is less than or equal to 6, and if I was to graph this right now, and I put x is 6, 1, 2, 3, 4, 5, 6, less than or equal to means it's a solid line, so I'm going to put that right there. And this, all of this area right here, would be the solution set to that. So the solution to that expression right there is a half of a plane. Okay? So if I was to go here, y is greater than 2. I'd go to where y is 2, 1, 2. It's not equal to, so what we do is we do a dash at that level, and we want to know where it's greater than, so it's everything that's above that. So again, another half plane, it just doesn't have a rigid boundary on that side. Okay, and that doesn't mean that the first solution's at 2.1 or at 2.000001. Technically, we just know that it can't be 2, so it's whatever's just beyond that, but numerically we can't reference that. So what happens when we have this, 2x plus 3y is less than 12? Well, it's a line if we treat it as an equal sign most. So let's pretend that it's an equal sign first. So we'll go ahead and go here, and I'm going to go ahead and do the cover up method. So I cover up the x's, pretend that 0 is implanted in for that. So then what times 3 equals 12? And that would be 4. So when x is 0, y is 4. So 0, 4, 1, 2, 3, 4. There's a point. And then I'll cover up the y's. And I get, in that case, 2 times what is 12? So that's 6. 1, 2, 3, 4, 5, 6. And then I ask you again, was it actually an equal sign? Was there a dash underneath in the beginning? And the answer is nope, there wasn't. So we need a dash line. Just like that. So it's going to be half a plane. It's either going to be above that line or it's going to be below that line. And if it gets a little bit more complicated, this is what we're going to choose to do. We're going to go ahead and pick a value that's not on the line and see if that's true. So let's pick this one, 0, 0. Okay? So plug 0, 0 in. 2 times 0 is 0. 3 times 0 is 0. 0 plus 0 is 0. Is 0 less than 12? Answer, of course, is yes. So if it's true for that point, it has to be true for every point. So then all of our shading goes like this. Okay? And this is all there too. All of that's in there. That's that region. Okay? So now we've got stuff that looks like this. So I've got a system now. So we're building in these inequalities. And that's what's going to lead us into this linear programming and what that means and why businesses all over the planet use things like linear programming to make decisions in terms of it. Yes, they use math to make decisions. So let's go here. So x squared minus 4 is greater than y. So let's try and do that one. So just a quick little sketch again. So x squared minus 4 is greater than y. So x squared minus 4, 1, 2, 3, 4. That's a parabola, right? It looks like this. And again, I don't know. Does it shade on the inside of it? Does it shade on the outside of it? I don't know exactly where is it. So what do? I check a point. So let's check 0, 0. So 0, right, 0. So I got negative 4. Is negative 4 greater than 0? Right, because I plug 0 into both of those. 0 into here and 0 into here. Is negative 4 bigger than 0? The answer is no, it's not. So if that's false, then all of those are false. Then this, everything out here, is our solution for that particular section. But this is a system, which means I need two things going on right now. So now I'm going to go ahead and do this one. So 3x plus 4. So I'm just going to graph the line 3x plus 4. 1, 2, 3, 4. right? Slope of 3, 1, 2, 3. So that is a line that goes like that, right? And it should be dashed. So we'll make it dashed. And you can see the origin's not on that line either, so let's check it. So 0, is that less than 4? Is 0 less than 4? And the answer is yes, it is less than 4. So that would be true. So that means I'm going to go like this. All right, and that's again dashed, dashed. So what's my solution? My solution to this is all of this stuff out here. My solution is where those two things overlap each other. So like this point right in here, this point, I'm going to call this A. This point is A. That doesn't work for either one of them, of those inequalities. This point right over here, B, that works for the top inequality, but not for the bottom inequality. And this point C right here, that works for the bottom inequality, but not for the top inequality. But this point over here, D, works for all of them. Okay, so that's what we're going to get into when we talk about this thing called linear programming, is solutions that work for multiple constraints. So what's the basics things here in linear programming? Let's say that I had a situation where I'm making something, making a certain product, and I know that I have to have a certain one variable. Let's say this is number of employees that I could hire. I cannot go past that. And maybe this right here is the amount of supplies that I can't house more than that in my warehouse. Okay? And maybe that I have to make a minimum of a certain amount of things based on my contract with the stuff. So that means that this line would shade down, and this line would shade down, and this line would shade up. And I know that it has to be positive, so this line would shade up, and this line would shade up, because I can't have negatives in any of those things. And then it looks like my super region right here would be this thing. That, what is this? Let's count it. 1, 2, 3, 4, 5. Looks like a pentagon. So that pentagon maintains or has all the solutions to this problem. And any of these things in here would work, any of these points in here. And there might be 25,000 different possibilities that I could have that deal with my employees, my supplies, and my minimum requirements for the stuff, knowing that I have to still be positive in both of my products for whatever I'm doing. Okay? Well, it turns out that I don't have to, in order to maximize or to minimize, because that's what businesses want to do. They might want to maximize profits, they might want to minimize loss, whatever it is. I don't have to check all 25,000 of these points that the max or the mins on these things. And again, I am streamlining a lot, but I'm hoping this helps. Max or the mins occur at the vertices of these locations. And look at that. What is the vertice of that location? Well, the vertice of that location is the intersection of two lines. And how do we find the intersection of two lines? We use systems of equations. Okay? And then I can plug that point, and this point over here, and this point over here, and this point over here, and this point over here that I get from doing my math, which I could use with systems and RREF or substitution or Cramer's rule or matrices or whatever. Whatever I want to do, I could use those points and plug them into what's called an objective function. What's my goal? Maximizing or minimizing stuff. Sorry, there we go. Plug it into this thing called an objective function, and we'll get a solution. We're going to find out which place is the best, the maximum or the minimum for that one. So that's the general thing. So what I'm going to do is I'm going to take T1 right now, and we're going to try and do it. But we're going to save a lot of time. Typically, we do these things by hand and graph them all out. But we are going to do this one here. That looks good. Yeah. We're going to do this one using Desmos. So if we were doing it on the graphing calculator, I'd have to solve for y, I'd have to solve for y, I'd have to solve for y, I'd have to put these things in, I'd find out where they intersect. But we're going to use Desmos right now, so let's go ahead and do this. Hopefully you have these copied down. If not, pause the video, copy those down right now. And because we can use Desmos, I'm going to go ahead and type those things into here right now. Okay? So you do the same thing, put it in. And this should work out. Desmos is really nice too because you can plug it in the form that we have there. So my first one is 3x plus 2y is greater than or equal to 20. So 3x plus 2y greater than or equal to 20. And you can see on my graph right here that I've already shown that this is a half of a plane, just like what we've done on our other things. So go ahead and give yourself a new line, and 5x plus 6y is greater than or equal to 52. And now you can see, and that's what's great about this program is, just like what I showed you a few minutes ago, points that are over here, right here in this area, those don't work for either of the inequalities. This one works for the red one, or the first one. This point right up here works for the blue one, or the second one. And all these points over here work for both of them at this time. So now I'm going to do a third one. And I'm going to do 2x plus 7y is greater than or equal to 30. Greater than or equal to 30. And now I have that. Good deal. Can you see that? And that's what's nice about this 4K camera, that it does take it down. I'm going to even focus it a little bit so that clears up a little bit. And then these last things says that x is greater than or equal to 0 and y is greater than or equal to 0. So that just basically means that we're in quadrant number 1. Okay? So I'm hoping that you see this, that the number of solutions is infinite. There's an entire possibility that goes out here of any of those things. So that means we're probably going to want to find a minimum because we can't find a maximum. Does that make sense? Because if it goes to infinity, it probably isn't going to be something that's maximum unless we have some negatives on our objective function. So what I need to do is I need to find out the points that are actually on these borders. So there's a point right down here. Do we see this one? That's where the x-axis crosses the green line. There's a point right here. There's a point right here. And there's a point right there. So there's 1, 2, 3, 4 points that we need to find out. Now I'm going to point to this one right here, and I'm hoping that you're going to make some logical sense with this. It's like, man, that's an intersection point, right? It is. It's an intersection between the red and the green. However, the blue doesn't fit in there, right? So it doesn't matter what this point is, it doesn't fit for the third constraint. So again, each one of these constraints could represent 3 different things. So what I'm going to do is I'm going to change these all now to equalities. And we're going to shortcut stuff here. Change them into equalities. And then we can just tap on the screen to find out those points. And it looks like I have to hit the delete button twice to get them. So now they're all equalities, and these are my points. And I need, in order to get the intersections, I still need to do x equals 0, x equals 0, and then y equals 0, so that I can have those 2 bottom lines. Okay? So then on my graph, I need this one right here, and that one is 15, 0. So I'm going to go to my little handy dandy sheet over here. Move this way a little bit. I'm going to go 15, 0. That's one of my critical points, 15, 0. And then I'm going to tap here and find that one. That one's 8, 2. So 8, 2, that's another one of my critical points. And again, if I didn't have Desmos right now, I would have to take the green line and the blue line, which is 5x plus 6y equals 52, and 2x plus 7y equals 30. and solve that using system of equations. Again, substitution, linear combination, matrices, Cramer's rule, whatever I want to do. But bam, I can just tap on it. I'm going to tap on this point right here, and you're going to go, wait, Mr. Bells, I can't use that point, can I? Remember, because that doesn't fit the blue. So blue might be something that I need to have in here. So I can't use that point. That doesn't do me any good. We do this one right here, 2, 7, 2, 7. That's a critical point. And then my last one right up here looks like 0, 10. So 0, 10. So you know that I have 4 points, 4 critical points in this thing. And at this point right now, my Desmos, I can take that and move that to the side and go, hey. So for each one of these situations, and again, I'm not giving you any specifics to this particular problem. We'll do that in just a second. But on this one right here, I have 4 critical points. And I'm going to try and find a minimum and a maximum based on this objective function, knowing that I also have from infinity to infinity, right? So this one could be really big. And you'll notice that my objective function right here is 3x plus 5y. Which means if I can go infinitely big on x and infinitely big on y, since both of these things are positive, the max is not possible. So there's not a possibility to maximize this out. Again, it goes towards positive infinity for both of them. Okay, but I can find a minimum. So let's try it. So if I plug those coordinates into this expression right here, 15, so that one gives me a total of 45. 8 times 3 is 24, plus 10 is 34. And 2 times 3 is 6, plus 35 is 41. And 0 times 3 is 0, plus 5 times 10 is 50. So it looks like if I'm trying to minimize my function, remember 50 is not really the biggest point. Remember, we can get towards infinities, right? Because 5,000 5,000s in here, or 50 billion is actually in this solution. Because remember, the little thing went that way, went towards infinities. But I can find a minimum, so that's right there. Awesome. So 8, 2 is my minimum requirement, which gives me a total of 34. And you're like, I don't know what we just did, but I'm hearing you. So then what would I need to talk about? I need to talk about something that was a little bit more real. And I'm going to go through this one. And this is, well, it's kind of big here. And what I have is, I don't want to say a super real one right now, but it's a little bit more legit. So I got a furniture manufacturer that makes chairs and sofas. So they're making 2 items from pre-packaged parts. So any of you have put together any solder furniture, stuff like that, or is that IKEA? They got a whole bunch of pre-packaged things that they do when you just assemble it. So this is a very simplistic approach to a linear programming situation. Okay, so a chair requires 2 packages of wood, 1 package of fabric, and 4 packages of stuffing. So there's 3 sets of supplies that go into the chair. Sofa requires 3 packages of wood, 3 packages of stuffing, and 2 packages of fabric. Awesome. So the same 3 things go into it, just different amounts. Again, we're trying to keep this simplistic so that we can do it still here. The packages are delivered weekly and the manufacturer has room to store. Ooh, so they have storage issues. So they can only store 1,300 packages of wood, 2,000 packages of stuffing, and 800 packages of fabric. The manufacturer earns $200 per chair and $350 per sofa. So what we're going to try and do is we're going to try and see if we can turn this written stuff up here into some mathematical inequalities like this stuff here, and see if it makes sense. And I'm going to go through this kind of quick, but remember, you have the awesome ability to say, hey, I'm going to pause this video and pull something off. So the first thing I'm going to do is I'm going to do objective function. So objective function is, it's a business, right? What does a business want to do? They want to make money. So they get $200 per chair plus $350 per sofa. And I'm going to use an F for sofa. I'm going to use an F for sofa. I hope that's okay. Just because my S's look like 5s, I don't want you to think, what's 3,505? What the heck is that? So then right here it says list all the inequalities that you found. So inequalities are constraints or limitations on the problem. So what I'm going to show you right now is this. I'm going to do some basic ones. I know that the chair must be greater than or equal to 0. I can't make a negative amount of chairs. I know that the sofas must be greater than or equal to 0. I cannot make a negative amount of sofas, which means that this relationship, the shading situation that we're going to do is going to put us all in the first quadrant again, because all the numbers have to be positive. Now you're asking, can there be things that have negative numbers? And the answer is absolutely yes. We're just not going to deal with them right now in our limited amount of time. So what are some other constraints? So my other constraints are on supplies, right? So I have a wood constraint. I have a stuffing constraint. And I have a fabric constraint. So I'm going to put those words right down here below this, because I know that and this is really tough, and again, 5 days, I'm trying to fit this into a half-an-hour video right now, so I'm cutting a lot of stuff out. The wood has to deal with C and F, so the chairs and the sofas. So I'm going to look up here in my handy-dandy little information package, and I'm going to look for chairs, wood. Chair requires 2 packages of wood. So 2 packages of wood for the chairs, right? I don't put a W in for wood. This constraint deals with wood. I know it's 2 packages of wood per chair. And then I go for sofa. Sofa requires 3 packages of wood. So 3 for the sofa. But I know that right down here, you see this right here? I only have 1,300 packages of wood, so that must be less than or equal to 1,300. And now I've got my wood constraint, my limitation for that. So now I'm going to do stuffing. So how much does a chair require for stuffing? 4 packages of stuffing. So 4 packages for the chair, plus how much for the sofa? 3 packages for the sofa, and that must be less than or equal to stuffing. 2,000. You see that? Less than or equal to 2,000. And then fabric. Fabric up here. 1 package of fabric for the chair. So, I mean, you're talking about an oversized stuffed lazy boy type chair. I mean, just gonna sink down in it. So 1 package for the chair, plus 2 for the sofa, because it's a little bigger. It's just not as cushy. 2 for the sofa, and that must be less than or equal to fabric, 800. Okay? So, this is where I'm going to let you go. I want you to be able to do this. Okay? So, it's my belief that if you graph these things, you're going to get, I've got 1, 2, 3, 4, 5 lines, right? So, if I have 5 lines, I'm going to do this over here. I believe that they might just kind of do this type of thing right here. And I'm going to get a, sorry, on the video. I'm going to get a pentagon. Remember, do not use this point or this point or this point. Don't use them. Don't use them, because one of the constraints doesn't fit. I might not have enough wood or stuffing or fabric for those things to be able to be okay. So once I get those 5 points, those are my 5 vertices, and I put those 5 vertices into these locations as I go around. Again, I have probably 5 or 6 of these different types of problems that I've used over the years, so I have different things for it. But then you're going to take and find those locations, right? So you're going to graph those things, you're going to plot the lines on it, you're practicing, and then you're going to find out what the profit is. And how do you find out the profit? Let's say that point A, it says to go clockwise alphabetically. So point A is 0, 0. Look at that. I already gave you one of them. Plug it in. So 200 times 0 is 0. Plus 350 times 0 is 0. So your profit at A is 0. And that makes sense. If you don't sell any chairs or any sofas, you don't make no money. Okay? So we need to be able to sell some stuff. So B, C, D, and E are all going to be possible situations for it. Remember, big picture thing. Everything in here is a possible combination of sofas and chairs that we could sell. However, a maximum or a minimum must occur at one of the vertices of what's called the feasible region. So hoping this will help you out. Again, one of my favorite lessons on these, and some of these problems take a long time, but they're pretty cool when we have, or at least cool for me, hopefully you guys are still staying strong with this and you want to be good at math. So you guys take care. Do this one out. This is one of the last videos that you'll see from Pre-Calc B. And stay strong. Stay on top of this stuff. Good job. Help each other out.